comparing physical properties. So why does ethanol have hydrogen bonding, whereas dimethyl ether does not? And what type of intermolecular force does dimethyl ether have? Pause this and draw a Lewis dot diagram to decide on the forces. So we can take a look at the Lewis dot diagrams here. And we know that there is bond polarity towards oxygen. These aren't equal and opposite, remember, because oxygen is bent. So this is a polar molecule simply because of the OH on the end. So it had London dispersion forces because it's a molecule. It also has dipole-dipole because it's polar. And it has hydrogen bonding because it has an O directly bonded to an H here. Dimethyl ether is also polar because of these two polar bonds here. Remember again, oxygen is not linear, so they don't cancel out. And this is polar. All right, so we have London dispersion forces and we have dipole-dipole because of its polarity. However, it does not have hydrogen bonding because oxygen is not directly bonded to a hydrogen. What type of intermolecular force does dimethyl ether have? Well, the strongest one it has is dipole-dipole forces. We're going to start with looking at the properties of ionic formulas. So a formula unit for an ionic compound is the lowest whole number ratio of a metal to a nonmetal in an ionic compound. So for instance, we're looking at sodium chloride here. We know that we write the formula for sodium chloride of having 1 sodium and 1 chlorine because sodium has a 1 plus charge and chlorine has a 1 negative charge. So to balance it, we just need equal numbers. And that's what we're representing in the ionic structure. So ionic compounds are a crystal, and it's not just 1 sodium and 1 chlorine connected. The crystal has multiple of each. However, as long as we make sure that we have the balance of the same number or the same ratio, we can say that it is still a formula unit. So we can have 10,000 sodiums so long as we have 10,000 chlorines there to balance it out back to a 1-to-1 ratio every time. So because we can have multiple, the attractive force between anions and cations doesn't just happen between one ion each. Ion attractions are non-directional, aka all anions attract all nearby cations. If we're looking at our diagram here, let's look at this sodium right in the middle. So the little orange balls have been labeled as a sodium ion. This is the structure for sodium chloride table salt. And if you look at it, it has a very cube-like structure, kind of like this. So each sodium is surrounded by a chlorine ion on each side. So we can have one on the bottom and the top of it, behind and in front, if you will, and side to side. So kind of like all directions on the Cartesian plane. So we have X, Y, and then this is actually Z, which is a little bit further than you guys know at this point, but it has one in each side three-dimensionally. Now, this is just a representation to show that it would continue in this fashion. So on the other side of this chlorine, if we kept coming outwards towards ourselves, we would find another sodium. And so you can see that each chlorine would then be surrounded by a sodium out here, sodium behind, side to side, up and down. Okay, so the attraction does not just hold one sodium to one chlorine. Sodium can be attracted to multiple chlorines, and chlorines can be attracted to multiple sodiums as well. So we talked a little bit about that as a crystal lattice. It's the arrangement of ions in a given compound in a repeating fashion. So ionic crystal lattices are what we were looking at earlier. And all they have to do is have some fancy structure, and it's repeating. It can be predicted, and it will look the same throughout. They just maintain their ratio of positives and negatives the whole time. Now, there's different ways that they can pack together and different arrangements they can have, and I said that they can be predicted. You do not have to know how to predict them in Chem 20. That is not what we are going to do. All we are going to say is that they may have different structures because of a few different things. There's a couple different reasons they can look different. They can have different charges or different sizes of ions in there. So anions and cations are arranged in this crystal lattice to maximize attractions to oppositely charged ions and minimize repulsions to similarly charged ions. Okay, so again, let's double back to what these can change. So charge, if I have a 2-to-1 ratio, I'm going to have to fit in twice as many positives as negatives. Therefore, that's going to have to work harder to minimize repulsions to similarly charged ions because there's so many positives. So they're going to have to arrange differently than perhaps our 1-to-1 ratio. Also, size. We looked at atomic size on our periodic table, and ion size follows very closely. So if we have really large ions and really small ions packed together, they can pack differently than two large ions. So let's think tennis ball versus marbles versus just two marbles together. How they can arrange themselves to minimize repulsions to their same type. So let's say we had another set of like a tennis ball and a marble here. These guys would be repelling each other so strongly, they're going to have to organize different than our positive and negative marbles would, if you will. So looking at this, all we have to do is decide why something may have a different crystal lattice structure. I've given you sodium fluoride. So this is sodium fluoride here. And this is calcium fluoride. Why do these have different crystal lattice structures? So our first thought should be ratio. The ratio of positives to negatives here is 1-to-1 because we require 1 sodium for every 1 fluorine. The ratio of positives to negatives over here is 1-to-2. We require 2 fluorines for every 1 calcium. Therefore, we must be packing twice as many fluorines in as calciums. So the difference here is because of the different ratios. We have 2 times as many negative ions to fit into the crystal. In this case, we have NaCl and CsCl. Why do they have different structures? So CsCl is here and NaCl is over here. Now this looks a little bit different, and the reason is this is just a repeating nature. This is called a unit cell. A unit cell shows the repeating nature. So if I were to take these corners and cube them off, like right, so I made a beautiful little cube, we would cut off the edges of these spheres. Now you have to use your math brain a little bit here. Okay, the corners of the spheres, if I cut them off here, this way I will have cut it in half. So I have a half, and then I cut it in half again. So I've got a quarter, and I cut it in half again. Each sphere, there will be 1/8 of a sphere left on each corner. So 1/8 of that sphere, 1/8 of this sphere, 1/8, 1/8. You kind of get the idea here. If I add all of those eighths up, I have 1, 2, 3, 4, 5, 6, 7, 8 eighths is 1 full chlorine, and you can see cesium in the middle here, so it would be completely entrapped by our cube. So if I put multiple of those cubes together, it'll start to recreate those spheres on the corner, and that's the whole idea of a unit cell, is that I could stack these cubes right next to one another and it would show exactly how they repeat. Now over here, this isn't a perfect unit cell, and the reason being, if I took this structure and put it right next to one another, I'd have a chlorine here and then I'd put another chlorine here. So this isn't a unit cell, this is just a representation of the crystal structure. Unit cells look wonky. Crystal structures make a little bit more sense just by what we're seeing. Okay, so why are they different? They are different. And the way we could see this is if you were looking at, I'm just going to clear off this guy here. These are like a perfect cube inside where we have a cubed corner here, cube corner here, cube corner, 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 and there's nothing in the middle. Okay, they're all connected on the edges. So if that's the case, this looks different because all of these corners would have been the same atom here. Okay, and in the middle I would have had one floating by itself. So they are different. Okay, so why are they different? Back to the actual question itself. So NaCl and CsCl both have 1-to-1 ratios. So it can't be the ratio here. Let's look at their atomic radius. So sodium and cesium are in the same group. Sodium has a smaller radius than cesium. Chlorines, because they're the same thing here, they're the same anion in both, are the same. So chlorine cannot be changing the structure here. All right, because they are identical size. Therefore, if we look at this, the reason that these are changing or different is not because of their ratio. They have the same ratio. It is because their cations have different radiuses. Radii, maybe? I don't know. English is not my subject of choice. So the cations have different radii, therefore that will affect the packing of this crystal structure. We also need to talk about the melting point and boiling points of ionic compounds and how they can be slightly different within the idea of ionic compounds. So there's a difference in melting point and boiling point for ionic compounds, and it depends on the magnitude of charges. Melting point / boiling point of binary ionic compounds. All right. So the magnitude of charges. So having something that has a 2+ versus a 1+ will have a different melting point. So the larger the difference between charges, the stronger the ionic attraction, and the higher the boiling point or melting point, either or. So I had an example here, and it says, which ionic compound will melt first? Magnesium oxide or magnesium chloride? So let's look at the charges, the difference in charges. Magnesium has a 2+ charge and oxygen has a 2- charge. So the difference between these on a number line is 4. Again, magnesium still has a +2 charge here, but each chlorine has a -1 charge. The difference between these is only 3. Therefore, based on this idea, magnesium oxide has the higher difference in charge. This is not electronegativity, it's just charge, and will have the higher melting point. Therefore, MgCl2 will melt first or lower. This difference in charges is actually quite significant. In the end, if you look up the melting point of each of these, as we started heating, let's say from room temperature, magnesium chloride is going to melt at 714 degrees Celsius, which is really high. I totally understand that. However, we're going to have to keep heating all the way to 2,825 degrees Celsius to get magnesium oxide to melt. So the difference in magnitude of charge, so difference by 1, gives a significant difference in their melting points. All right. Something we haven't talked about yet are network solids. Network solids are atoms, typically of the same element, that are covalently bonded into 2 or 3D structures. The best example is carbon. It has so many different arrangements. Carbon can be present in so many of these different ones. Network solids are usually very hard, and they have much higher boiling points than molecular compounds and ionic crystals because they don't have intermolecular forces. They are covalently bonded the whole way through. They are brittle though. Now, brittle doesn't mean that they aren't hard. So they can be very, very hard and strong, but they can be brittle because they break. They don't bend under pressure. There's no give because they are all covalently bonded together. Here are our common network solids. So we have graphite, and often its formula is written as C graphite for a state because carbon can arrange itself in so many different ways. This next one is diamond. And again, if I want to represent it, it's C diamond. And it's the best representation of like bonding in all directions. So each one of these represents a carbon atom. And we can see that this carbon atom is connected to 4 other carbon atoms. It's in a tetrahedral shape, so this is 3-dimensional. Then this carbon would be connected to 4 other carbon atoms here, here, and then there would be another one coming out towards us this way and out towards us this way. It's not drawn. Then this carbon is connected to 4 carbon atoms, you can see, and this is connected to 4. We'd have 2 more this way. It would just repeat in that fashion, okay? Every carbon is covalently bonded to 4 carbons. So there's no need for intermolecular forces to hold this part of the diamond to this part of the diamond to this part of the diamond. You can't actually differentiate parts of the diamond. They are all connected equally and very, very strongly. Over here we have a buckyball. So each carbon is actually connected to 3 carbons here. And they wrap around in a big circle, if you will, or a sphere. So see bucky ball. And this is a nanotube. The nanotube is like a buckyball that's been cut in half and then just extended in between. All right, so it's like a long cylinder in between here that's a wrap of carbons all the way around, and then buckyballs for ends. So see nanotube. And last but not least, so those were all of our carbon ones. The other one that we talk about is silicon dioxide. So this is glass. So silicon dioxide is the formula we write. However, it's like an ionic crystal in that it keeps repeating. All right, now let me just think about this. So this is silicon, and it is connected to 2 oxygens here. Then we have another silicon that is connected to 2 oxygens, and another silicone that is connected to 2 oxygens, and you can see how they keep repeating. However, instead of drawing it as SiO2 like this, we know that it's actually connected in a 3-dimensional structure where it continues to repeat. So this was our original, and this Si is connected to 2 more oxygens, and then it's connected to another silicon dioxide compound. So it just repeats in a 3-dimensional fashion. It's the only one that we will talk about. I think your textbook has one more included. Take a look through the pages for this topic. There is one other that they talk about. You want to be able to recognize these by formula and by name, in that they are a network solid, and that makes them their own special category. So we won't classify them as ionic or molecular or atomic. We classify these all as a network solid. They get a special label. So network solids, like I said, have continuous bonding, holding every entity or every element in the crystal together. Atoms are held together by covalent bonds. There are no intermolecular forces. So in order to melt these, we have to break covalent bonds. We have many of them to break, which requires considerable amount of energy. Covalent bonds are very strong. These melting points are very high. Electrons in covalent network solids are either held as core electrons or in lone pairs in the bond. So think about carbon. Carbon has 2 core electrons and it has 4 bonding electrons. Now in diamond, of course, this carbon will have shared another electron here. So their electrons are not free to move. Okay, they're either stuck in a bond or stuck in their core electrons deep within their shells. In either case, these are not free to move through the network, and this is why it does not conduct electricity. So, let's compare all of this. So we know that we have ionic compounds, we have network solid compounds, and we still have covalent compounds. And covalent compounds have intermolecular forces. We don't really talk about breaking covalent bonds. Once we have a covalent compound, we're breaking those intermolecular forces for phase changes, okay? We are not talking chemically breaking these bonds. So what we know is that we've got 3 intermolecular forces. There were London dispersion forces, dipole, and the strongest were hydrogen bonding. The stronger the intermolecular force, the more difficult it is to move these molecules apart. Now, an intermolecular force is weaker than these 2 forces, okay? So we're just moving 2 molecules, for instance, of carbon dioxide apart to change state. We are not breaking the bonds within. However, if I want to move a sodium away from a chlorine in sodium chloride, I have to break the actual ionic bond between them to move them apart. To move the atoms in a network solid apart, remember, like diamond, again, it continues on in a full 3-dimensional structure. If I want to move them apart, I have to break the covalent bonds. So over here, we were breaking intermolecular, whether it was one of these 3. If I want to heat up and change state of an ionic compound, I have to break an ionic bond. And if I want to change the state of a network solid, I have to break a covalent bond. All right. The stronger the force, or the stronger the bond, the higher the boiling or melting point, the higher the surface tension, and the higher the viscosity. Viscosity means, remember, resistance to flow. So if something is very viscous, it means it is thick, and it would have strong forces holding it together. If it is not viscous, it is very thin, and it would have very weak forces. We can also talk about volatile. Volatile means tendency to evaporate. So if something's very volatile means it evaporates easily, meaning it breaks its state and it changes to a gas easily. So it's very volatile. It has weak intermolecular forces. So the less volatile a substance is, okay, the stronger the intermolecular forces, kind of the opposite of what we wrote here. A volatile substance has a high tendency to evaporate. So let's go through the order of forces, or the strength of forces. It is hardest, or takes the most energy, to break a network solid because you have to break covalent bonds. And you have to break many at once. You can't just like break one, remember, because they are connected in 3 dimensions. So many covalent bonds have to be broken at once. Now we put kind of metals and ionic compounds on the same level here. Metals and ionic compounds, to break those or move those elements or ions apart, we have to break the metallic bonds or we have to break the ionic bonds. Either way, it's a lot of work, not quite as much as these covalent bonds because there are so many that we have to break at once in that network solid. Okay, once we get past those two, once we get into molecular compounds, we are not breaking the covalent bonds. We are moving molecules apart. Breaking intermolecular forces. Now, the strongest intermolecular force and the hardest one to move apart would be something with hydrogen bonds. Next up would be dipole-dipole, and the weakest is London dispersion forces. Okay, so something with London dispersion forces takes the least amount of energy in the whole group to move apart, or to boil, or to melt, all of those. So let's put that all together. Let's order the following from most to least viscous. Explain your reasoning. So I've given you the kind of ball and stick structures here. The black spheres are carbon and the white spheres are hydrogen. So let's just count to get our formula here. I have 1 carbon in the center here, 2, 3, 4, 5 carbons. So C5. And then on each of these outer carbons, I have 1, 2, 3 hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. H12 is its formula. Same counting over here. We're going to go 1 carbon, 2, 3, 4, 5. And hydrogens, where there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think you may see where we're going with this. They all have the same formula. Okay, so just carbons and hydrogens. We know that all of these are non-polar. All right, so we have our diagrams. We've decided on their polarity. Let's list their forces. These are all covalent and non-polar specifically. Therefore, they all have London dispersion forces. They do not qualify for dipole-dipole because they're non-polar, and therefore they cannot be considered hydrogen bonding either. Okay. We have all things that have London dispersion forces. So the first thing we want to check is their total electron count. So 5 carbons, each carbon has 6 total electrons. That's 30 plus 12 is 42 electrons total. Now they're all going to have the same number because they have the same structure or formula. Therefore, the last thing that we could check to decide who has the stronger London dispersion forces is their shape. Remember, this is the spaghetti versus macaroni. And so that's why I've drawn it kind of, or put these representations in for you. So looking at these, dimethylpropane is quite branched, if you will, meaning the central carbon is connected to 4 other carbons. This one is like long and skinny, and this one is slightly branched. It looks kind of long and skinny and has this 1 extra here. All right, so this is the most spaghetti or marker of the 3, my bad. And this is the most macaroni or marble of the 3. Okay, it's more spherical than this one. It's kind of weird, and this one's long and skinny. All right, so Most viscous to least viscous is what we want to write. To be quite viscous means it has strong intermolecular forces, and to be not very viscous means it has weak intermolecular forces. Something with the strongest intermolecular forces has the greatest surface area. So our spaghetti or marker compound has the larger surface area for attractions. Therefore, propane will be the most viscous. In between will be this methyl butane. And our least viscous is the one that is doesn't have as much surface area for interaction. So it'll be our 2,2-dimethyl propane. These are structures that we would look at and name, etc. in Chem 30 for organic, but using their ideas here for their shape is what we're looking at. Okay, so we based our answer on surface area for attraction. Next up, rank the liquids above from highest to lowest surface tension. So let's just draw ourselves a structure here. We're going to do highest surface tension and lowest surface tension. Notice how I always make myself a little line. And I always write where's the strongest intermolecular force and where's the weakest, because often you guys are really good at deciding what the intermolecular force is, but you just order them the wrong way. So if it has a high surface tension, it means it sticks together really nicely. And that means it has a strong intermolecular force. Therefore, this must be a weak intermolecular force. First things first, decide on your intermolecular force. So we need to draw a Lewis dot diagram for each of these. I'm just going to pause and draw them, and then we can double back to this together to talk forces and order them. All right, so we have all of our compounds drawn now, and we're going to decide if they're polar or nonpolar. So because bromine is bonded just to bromine, the difference in electronegativity is 0. This is a nonpolar molecule. CH3OH is polar because of this oxygen. C2H4, just carbons and hydrogens, is nonpolar. And CH2O is polar because of the C to the O here. With that, let's assign some forces. Something that's nonpolar only has London dispersion. All of these are molecular, so they all have London dispersion forces. Let's just see if they have anything else. Because this is polar, CH3OH, it also has dipole-dipole. And because of this O to an H bond, it does meet the criteria for hydrogen bonding. So a hydrogen bond is the strongest force in that molecule. C2H4 is nonpolar, so it just has London dispersion forces. And last but not least, CH2O is polar, so it has dipole-dipole. It does not meet the criteria for hydrogen bonding because this oxygen is not directly connected to a hydrogen. All right. Now, the last thing I need to do is I can see that we have 2 London dispersion forces. And I need to be able to rank those 2. So let's take a look at their total electron count. Each bromine here has 35 electrons. So the total electrons here is 70 electrons. 2 carbons, each carbon has 6 electrons. So 12 plus 4 from all of those hydrogens is 16 electrons. Because bromine has more electrons, therefore it has stronger London dispersion forces. You need to make a statement like that if you have 2 that have the same force. All right, let's rank them from highest to lowest surface tension now. So the strongest intermolecular force here is hydrogen bonding. So CH3OH should have the highest surface tension. Next up will be something with dipole-dipole. So our CH2O. Bromine has stronger London dispersion forces than C2H4. Therefore, bromine is up next. And last but not least is our C2H4. This should be the order of our molecules from highest to lowest surface tension. Rank the following compounds from highest to lowest melting point. So what I'm going to go through and I'm going to do first is I'm going to decide, because I can see here they're not all molecular. So I'm going to classify as ionic, a network solid, or covalent first. Okay, or elemental. So He is just helium. It's a noble gas. It likes to be by itself. It's an element. SiO2 looks covalent. However, it was one of those network solids that we talked about. NH3 is covalent. BaCl2 is ionic. CO2 is covalent. And CH3Cl is also covalent. From there, I need to take a look at my covalent compounds and decide on their structures. So I'm going to draw a Lewis dot diagram for each of those. I don't need to draw a Lewis dot diagram for a network solid or an element or an ionic compound. They don't get assigned intermolecular forces. So we're done. This is the strongest force possible there for those guys. CO and CH3Cl. All right. So elements have just London dispersion forces. They aren't polar, they aren't polar, they're non-polar, they are a London dispersion force. We need to decide if NH3 is polar or non-polar to decide on its forces. NH3 is polar. If you go through, CO2 is non-polar and CH3Cl is polar. Deciding on forces, this one has, London dispersion forces. It also has dipole-dipole, and it meets the criteria for hydrogen bonding. CO2 is non-polar, so it just has London dispersion forces, and CH3Cl has London dispersion forces and dipole-dipole. It does not meet the criteria for hydrogen bonding. We have two things that have London dispersion forces, so we need to look at their total number of electrons. Helium has 2 electrons total. It's just an element, whereas CO2 has 6 plus 8 times 2. That looks like 22 electrons. So CO2 has more electrons, therefore stronger London dispersion forces. Okay, highest to melting point, lowest melting point. So highest melting point means it takes lots of energy to separate. Therefore, they have strong intermolecular forces. And the lowest boiling point, or melting point has the weakest intermolecular forces. See, too many eyes there. Okay, the strongest force here, and I guess I shouldn't be so specific as an intermolecular because we have things that are intramolecular. So the strongest force. The strongest force here is a network solid, so SiO2, and I'm just going to check them off to make sure we add them all. Next up is BaCl2. It's ionic. Remember, ionic and metallic could be considered the same. I won't give you both, but if I had just a metal here, you'll want to include it as a metallic force. Next up is hydrogen bonding. NH3, dipole-dipole, so CH3Cl. And last but not least are 2 London dispersion forces. CO2 has larger or stronger London dispersion forces than helium. This should be our order of atoms. Conductivity. For something to conduct electricity, there must be the ability for charged particles, so either positive or negative ions, or free little electrons to move. So for example, compare the conductivity of solid ionic compounds, molecular compounds, and metals. So what I'm going to do is I'm going to look for a few things. I'm going to draw a chart to compare these. It might be a little bit easier. What we're looking for, we're going to compare a solid Ionic, that's important to decide. Molecular and metals. And we're going to look for free ions, so those positives and negatives, and free electrons, so not in bonds. And that will tell us if they conduct or not. This is kind of like a little chart in your notes if you're looking. All right, solid ionic compounds. We have positives and negatives held in that crystal lattice. Are they free to move? No. So there are no free ions. Are there free electrons floating around? No. Electrons have been transferred to create those ions. And those electrons, remember, let's say fluorine is involved. Those electrons were transferred to fluorine to fill its octet, and fluorine is going to hold on to those electrons tightly. And let's say it was bonded with sodium. Sodium gave up its outer electron. Ooh, it looks like that's covalently bonded. Sorry, that's not what I meant to do there. Sodium gave up its outer electron to fluorine. So there's no free electrons. They've been transferred. If there's no free ions and no free electrons, there's no charged particles that are able to move. Therefore, this does not conduct electricity. Molecular compounds. Are there free ions? Well, there's no ions to begin with. We have never talked about a full positive, full negative, and we've never drawn square brackets around everything here. So there are no free ions. Are there free electrons? Well, that's also a no. They're either stuck in a lone pair in the core of these compound or elements, or as bonding electrons, but none of those are free to move. So this is also a no. If it has no free electrons and no free ions, there's no charged particles that can move, it will not conduct. Last but not least, we have our metals. Remember, those were positive cations, kind of organized like this with their electrons hanging out around. Are these ions able to move? Not really. Okay, they're kind of stuck in that arrangement of being really nice and flat here. Are there free electrons? There sure are. Remember, they are delocalized, or they're in a sea of electrons. So if they have a yes somewhere, they have a free particle that is able to move, and it will conduct electricity. So solid ionic compounds have no free charged particles. Molecular compounds have no free charged particles. And metals have free electrons so they can conduct. There is some practice in your textbook if you want to take a look at it in terms of ordering compounds based on their properties and getting familiar with the idea of a crystal lattice and network solid.